Welcome to the Mechanics of Solids lecture series. In the next series of videos we'll be looking at torsional stress and rotation in circular shafts. In particular, our lesson objectives are to be able to compute rotations or angle of twist and shear stresses in circular and tube-shaped shafts arising from a variety of loading conditions. Some examples that we'll look at are a single shaft subjected to an end torque and gear shaft subassemblies with internal torques. And here's the first example we're going to look at. Shaft AB, that's the shaft between these 2 points, is made of a circular tube with a length of 200 millimeters, an outer diameter of 30 millimeters, and wall thickness of 1 millimeter. The shaft material is a red brass with G shear modulus of 40 gigapascals. The shaft is attached to a 300 millimeter long crank handle, that's this handle, with a force couple applied at the ends. You could apply that force couple with your hands if you were turning the crank. Okay, so let's go ahead and summarize some of the given information. We were given that the length of the shaft, I'll go ahead and draw that on this figure, call that L sub S. The length of the shaft is 200 millimeters. The length of the handle, and we're going to need to keep these straight when we're working the problem. The length of the handle, I'll call that LH, is given as 300 millimeters. Okay, we are also given a diameter of the shaft of 30 millimeters, a thickness of the shaft, because it's a tube section, not a solid circular section, thickness of 1 millimeter, and the shear modulus of the material 40 gigapascals. Okay, so in part A we are to find the maximum couple force that can be applied to the handle just before the material starts to yield. And we'll take the yield stress to be 100 megapascals. So to summarize, for part A, we are asked to find a force, the maximum force, so that tau max is no greater than tau y. Tau max is no greater than 100 megapascals. And typically I would solve for force in kilonewtons, but in this problem we'll see that the force that you could apply by your hands to this handle is a relatively small value, so it's more appropriate to solve for it in newtons. I could go either way on this problem, however. So first of all, let's find a relationship between the force or the applied couple here and a torque. Hopefully you recognize that each of these forces are going to apply a torque to this shaft that's equal to the value of the force times the arm between the lever arm between the applied force and the shaft. And I'm going to draw that as a couple. You can see that here, a couple torque acting in the outward direction. Okay, so relative to the force, torque is equal to 2 times the force, because there's 2 of them, times the lever arm, which would be LH over 2. However, this simplifies to F times LH. Okay, now let's go ahead and note our equation for the maximum shear stress as a function of the torque. Tau max is equal to TR over J. We can substitute in our expression for T F times L sub H times R over J. Okay, the next thing I'm going to do before I start solving for anything is try to identify or isolate F. So I'm going to rework this equation a little bit. F is equal to tau max times J divided by L sub H times the radius R. So now I have this in a form that I'm ready to work with it. And units, I'm going to go ahead and note my working units before I proceed. as many problems that we do in SI units, we're going to use working units of newtons, millimeters for length, and megapascals for stress, noting that a megapascal is a newton per millimeter squared. Okay? Most of these variables are easy to identify. Let's spend a little bit of time thinking about this J, the rotational inertia term. So, since it's a tube section, I need to use the formula J for a tube section equal to pi over 32 times d to the fourth, that's the outer diameter, minus d, little d to the fourth, which is the inner diameter. You could also work in radius. For this problem, I'm choosing to work in with the diameters. So let me draw a picture of the tube section. Remember, we were given that the outer diameter, d, here is equal to 30 millimeters. Okay? It's a tube section. We're given that the thickness of the tube here is 1 millimeter. Thickness of the tube over here is 1 millimeter. That tells us that the inner diameter is 28 millimeters. Okay, and this is really important to pay attention to. This is a common error to assume that the inner diameter would, if the wall thickness is 1 millimeter, that the inner diameter would be 29 millimeters. So just be careful and think through the problem. It's always good to draw a sketch. Knowing those, we'll proceed. J is equal to pi over 32 times the outer diameter, 30 millimeters, to the fourth, minus the inner diameter, 28 millimeters, to the fourth. Notice the units would be taken to the fourth as well, as we expect to have our rotational inertia in units of length to the fourth. Carrying this out to 3 significant digits, J is equal to 19,200 millimeters to the fourth. Okay, now I think I can evaluate F. F equal to the maximum stress, 100 megapascals, times the J value, 19,200 millimeters to the fourth, divided by L sub H, the length of the handle, 300 millimeters, and times the radius, which is simply our outer diameter, divided by 2. Okay? All those numbers multiplied together, it's 426. Let's look at our units carefully. A megapascal is a newton per millimeter squared times millimeter to the fourth. On the bottom we have millimeters squared. So this millimeter to the fourth is canceling out with these two, and we're left with 426 newtons. Okay, let's switch to another sheet to work part B. From A, we note that the force was 426 newtons, which we just solved for. Part B says compute the angle of twist of the handle when subjected to the max couple from part A. Assume the shaft to be fixed at point A. So that we want the max angle of twist at point B. Basically we want the relative rotation along the shaft, which can be evaluated from the formula phi equals TL over JG. This is our formula for angle of twist or torsional rotation. Substitute the couple for the torque, F times L sub H. Now, which L do we want here? This is the length of the shaft. So, as we mentioned before, very important to keep those separately, but the rotation is along the shaft, so we use L sub S. Divided by jg. Okay, inserting the numbers. F was 426 newtons. L sub h was 300 millimeters. L sub s was 200 millimeters. The J value from the previous page, I didn't write it down, was 19,200 millimeters to the fourth. And our G, let's go ahead and convert G, since our working units, again, newtons, millimeters, and megapascal, convert G to megapascals by multiplying by 10 to the third, 40 times 10 to the third megapascals. And the numbers multiplied together would be 0.034. And look at our units here. We have a Newton per millimeter to the fourth. Okay, so first note that these millimeters and these cancel out. Millimeters squared on the top, millimeters to the fourth on the bottom. Now we have a Newton per millimeter squared on top and a megapascal, which is a Newton per millimeter squared on the bottom. So those also cancel out. And the result is unitless. The units are actually radians, equivalent to unitless. So we get phi is equal to 0.034 radians. And our reality check for a problem like this would be that our force is relatively small in the correct units, something that you could expect to physically apply with a hand crank. And the rotation of 0.034 radians is also relatively small.